Hello, YouTube! Today we're going to be talking about free body diagrams, gravity, and normal force. This is pretty much just taking the extension of what we did last time, saying, okay, well, how does it actually work for stuff in the real world? By which I mean the oversimplified world that we live in for this class, and also how do we actually set things up and draw them and keep track of them so it looks a little neater. So, in particular, if you're able to draw free body diagrams for an object and you're able to predict which forces are going to be on the object based on like the description or the problem, you're in really good shape. The way to do that is to identify which forces are on the object. There's going to be a couple ones that are sort of hidden forces that might show up, but mostly the problem will just tell you about them. And then also being able to calculate the gravitational force of an object that's on the surface of the Earth. That'll get a little different when you're off the surface of the Earth, and we will eventually get to that, but it'll be a while. And then last up, as long as you can define normal force, find normal force, and be able to set it up in a problem, you're in great shape. So, what's a free body diagram? I'm going to be abbreviating this as FBD from here on out. Because it's a lot of writing and I'm lazy. But a free body diagram is a diagram of a body that is not attached to anything, or a thing that is not attached to anything. So it is a picture of a thing that's not attached to anything. And in particular, it's basically just a way to draw an object and show which forces are on it, so you can really keep track of everything that's trying to make this thing accelerate, so that you can figure out what the force on it actually is and what that force is doing once you've found that out. So first place you're going to start with all of these is dot. People tend to really like that step just because basically every time we're like working on a problem and someone's like, I'm stuck. I'm like, we'll draw a free body diagram. And they're like, I don't know what to do. And I'm like, first step. And they're like, dot, because it's a starting point, right? You have an anchor that you can at least cling to and feel like you know what you're doing. From there, the big one is that you should be drawing an arrow for each force that's on the object and then label that arrow with which force it is. These are my conventions, by the way, and these are conventions that are somewhat widely held. If other people do it slightly differently, that's honestly fine, but these are also the conventions that the AP exam uses. For the most part, we'll get to the one big distinction at the end. So just really, I guess make sure you're doing it based on these conventions, because the AP exam is really going to care if you're not. So starting out with a dot, from there, it's really big that you are drawing your forces as arrows that start on the dot and go away from the dot. If you have multiple forces going the same direction, that can sometimes get a little messy. That's fine. Just make sure that you label them separately and just make your dot a little bigger so that you can fit it. Maybe your dot's a little more of a circle. It's fine. Ways that I have seen people do this that wind up being wrong, and you want to be careful of. Don't draw your arrows pointing at the dot. That one's gonna get marked wrong on the AP exam. Even if something's pushing the thing, draw it on the other side, showing what the thing is feeling. You're not focusing on what other stuff is doing to it. You're focusing on what the thing is feeling the other stuff do, if that makes sense. The other big one is if you have two arrows going the same direction, don't stack them. The big reason for that is that this looks ambiguous. It's really hard to tell if this is one long arrow traveling through another arrow or if these are two arrows. So do not stack your arrows like that. Really just dot, arrows going away from it. From there, AP exam is going to have you not break it up into components, but for this class, because of the whole thing with the net force from last time, once you've got your arrows drawn out, most of the point here is so that I can keep track of what the components are. I think the convention I've been using in my arrow answer keys is that the X component is blue and the Y component is red. I'm going to try swapping colors around until I find something that lets me do that. Great. So from there, break it up into components, and a lot of times what that'll look like is something like this, where you're saying, okay, well, my normal force in the Y direction is this, and my normal force in the x direction is this. So put a second subscript under this, whatever subscripts you have to say which force it is, for the x direction or the y direction. I tend to like labeling things so that you've got like letter and then a little baby letter next to it telling you which of those things it is, because that tends to be easier to remember that it's a force and tends to be easier to remember which variable you want to put it in for in the equation. Also, it works better when you have a bunch of different things and that have weird names and you want to still have a convention that lets you keep track of it. So these are some forces that we're going to come across a lot as we're going. So I just wanted to talk about them. And so let's do it. First up, we've got gravity. Turns out all objects in the universe are attracted to each other at all points in time. So if I have any two things, my fist and my other fist, they're actually getting pulled together by gravity. Now, the force of gravity is insanely small, unless you have insanely large objects, because the bigger the things are, the more strongly they're attracted to each other. The force of attraction between the Earth and any object on it is going to be based on the mass of the Earth, which doesn't change, the mass of the object, which does change, and the distance the object is away from the center of the Earth, which when you're on the surface of the Earth is pretty much the same everywhere, compared to the size of the Earth anyway. So, because most of those things are the same, the only one that's going to change it is the size of, and specifically the mass of the object that's you're figuring out the force for. So, Fg is the force of gravity between the object and the Earth. Notice that it's not just the force of gravity on the object from the Earth. They're actually both feeling that force, and we'll get to that more with Newton's third law. This is called weight. So if something's like, what's the weight? What they're telling you to do is just do mg. If they're saying, what's the force of gravity? What they're telling you to do is just do mg. That's it. M is the mass of the object. It's technically a measure of inertia, meaning how hard something is to accelerate. It's only going to depend on the amount of stuff there is, not the planet you're on. So if you go to the moon, your mass isn't different because you have the same amount of stuff. Your weight will be different because the moon will be pulling you a different amount than the Earth would, but your mass will be the same. G is on Earth always 10 meters per second squared down. What G is the acceleration constant of gravity on Earth. It's also referred to as the gravitational field on Earth. And where that comes from, where that 10 comes from, is the distance from the center of Earth, which is pretty much always the same, the mass of the Earth, which is pretty much always the same, and some gravitational constant that's like, hey, how strong is gravity in our universe? And that's always the same as long as you're in the same universe. So in particular, the way this is going to show up for problems in this class, every time you're doing a free body diagram, dot, line going straight down for force from gravity. And honestly, I would skip straight to just making its size mg. If the problem tells you the weight of the object, that's the size of the force of gravity. If it tells you the mass of the object, just go straight to doing mg. Don't worry about g being a variable. Yes, you're writing it with a letter, but that's because the letter is easier to write than 10, and because it would still work even if you were on the moon, which has a different number than 10. I think it's actually 1/6 of 10, roughly. All right. Oh, real quick, you might have heard other people use gravity as 9.8. That's fine if you prefer doing that, but if you're doing that, I don't know why you're not using 9.812 or 52, I think, and then just continuing to go from there. It's not a precise number, and going there's a 2% error going from 9.8 up to 10, and that 2% error for all the calculations we do in this class is well worth being able to use 10, because we have 10 of these, which means, most humans have 10 of these, which means that normally societies wind up getting a number system that's based off of resetting when you reach 10. That's not true of all societies, that's not true of all number systems, and that's certainly not true of all people, but the one that we use for this class is base 10, so it gets a lot easier that it's just conveniently 10. Normal force. So if you've taken another physics class before this one, you've probably heard of normal force, and you might accidentally have thought of it as like the thing that balances out gravity. Sometimes, yes. But in reality, normal force is simultaneously simpler and a little weirder than that. So what normal force is it's the force that stops things from going through each other. In particular, and this is why it's called the normal force, it is always perpendicular to the contact surface between those two objects. So if I have my two hands and they're pushing against each other, the surface between them will be like this. The normal force will always be perpendicular to that. So the way the pen is going. If I rotate my hand like this, the normal force will go off at a diagonal. If they're pushing like this, the normal force will be sideways. If they're pushing down, the normal force will be down on one and up on the other. So normal force is not always just straight up. It's not always the opposite direction as gravity. It's whatever direction it needs to be perpendicular to the way the two things are pressing against each other. That holds as well if it's a curved surface. It'll be perpendicular to the tangent line. So if my hand is pushing on the water bottle, the force on my hand will go the direction of the pen. The force on the water bottle will go the opposite direction, even though it's a curved surface. The one thing that's weird about it is it's however big it needs to be to stop objects from going through each other. So if I have this pen and I push it up like that, the normal force on the pen will be bigger than gravity because my hand is trying to go up through the pen. And if the normal force was the same as gravity, then the object would be not accelerating, it would be balanced, and the pen would go straight through my hand. In order to get that to not happen, the normal force has to be bigger to make it balance out. That should be it. Whoops, typos. There is technically a maximum to normal force, because what happens when you reach the maximum normal force on an object is that the object breaks. But for this class, unless we're explicitly trying to figure out whether or not something breaks, don't worry about it. Normal force can be however big it needs to be. Normal force can't be negative, though. You can't ever pull with normal force because it's trying to stop things from moving through each other. If I lift my hand, this pen off my hand, then there's not any normal force on it from my hand. And my hand's not going to... if I push the pen into my hand, the normal force will get bigger because it needs to stop the pen from going through my hand because there's something else trying to push it through my hand. If I pull the pen off my hand a little bit, but not all the way, then because I'm pushing up against it, it's not being pushed into my hand as much by gravity anymore because I'm balancing out some of that. So you'll have less normal force. If I do that enough, eventually it'll lift off my hand because there's no normal force. You won't suddenly get the normal force yanking it down to keep them stuck together. Whenever you're using a scale, what that scale is telling you is actually not the object's weight. What that scale is telling you is the amount of normal force it's putting on you, which is why if you're on a scale and you lean back against a counter, the scale will read a smaller number, or if you push into a counter, the scale will read a bigger number. It's because, again, the scale doesn't actually tell you your weight. It tells you how much force is getting pushed into the scale. So, when you're drawing free body diagrams, and you need to find your net force. In particular, big steps. Start with a dot. If it's on Earth, draw an arrow for gravity. If it's touching anything, draw a normal force perpendicular to the surface for each thing it's touching. One for each thing it's touching. I really should just pay for the function that lets me type with this thing. But I am a cheapskate. So, I also did directly type it below hand. Anyway, I know my slides. The other big one is that you just want to draw an arrow for each other thing that's touching it. If something's not touching it and it's not using gravity, don't draw an arrow for force. You, by and large, will not be able to... put a force on something unless you're directly touching it. Once you've done that, break everything up into x and y components. Add up all your x components. That'll be your net force in the x direction. Add up all your y components. That'll be the net force in the y direction. Keep those two things separate, but have both of them. One of the other big things is that if you know that the forces in a given direction are balanced, or you know that something's not accelerating in a given direction. So a situation that comes up a lot is something will be on a surface and it won't be, and especially if it's moving to the side. If it's moving sideways, then it could be accelerating sideways. It depends on whether or not it's going at a constant velocity. But it's definitely not accelerating up and down because it's not moving up and it's not moving down. So if you're not moving up and you're not moving down, and you don't start doing that in either direction, then you're also not accelerating in either of those directions because your velocity is staying 0 in the y direction. So you will have no acceleration in the y direction. And that happens all the time. Most of the problems we do, though not all of them, you'll have no acceleration in the y direction and no net force in the y direction as a result. So let's do an example. We've got a 30 kilogram box that's being pushed at an angle of 40 degrees above the horizontal with 50 newtons of force. I'm going to change these numbers really quickly. This should be a 40 kilogram box. I don't think I accidentally made the problem so that we're lifting it off the table, but I want to make... Oh, it was good either way. Whatever. This is fine. So, first step is to find the normal force on the box if it's not falling through the table. And the second step is to find the net force on the box, just period. So let's take that, let's make our picture, and we'll go from there. So we've got a box. And we know that it is a 40 kilogram box. We know that it's getting pushed at an angle that is 40 degrees above the horizontal with a force of 50 newtons. And A is asking us to find the normal force on the box. The way normal force gets written is F subscript N. I should actually have that. So Fn is normal force. F subscript G is gravity. I also just write that as mg most of the time because, again, it just kind of saves a little bit of writing. And B is asking us for the net force on the box. So let's do it. All right, well, first step for all of these, free body diagram. So I'm going to start out with my dot. Next, I need to think about all the forces that are on it. There's going to be one force for each thing that's touching it, one force for any forces that are given. I'm going to go ahead and call this one F1 because I don't have a better name for it right now. And one force for gravity if it's on Earth, which it is. So I'm just going to go ahead and put in the gravity. And I'm going to go ahead and label it with the size just so that I remember that's how big it is. Gravity is always mg. Again, g is just always 10, so it's just mass times 10 every single time. I also know that it's being pushed by this thing at a 40-degree angle. Immediately, I'm just going to break this up into components. We're going to have an x component, and we'll have a y component. Our x component is going to be equal to the diagonal, which is 50 newtons, times the cosine of 40, which is 38 newtons. And doing that again with the sine will give us the y component. X and y aren't always, as we saw in the last one, going to be sine and cosine and sine respectively. It'll depend on which angle you're given, but a lot of times angles are measured from the horizontal, and in those cases, that's what winds up happening. So people tend to develop a habit of just assuming that sine is x and cosine is y. Just be careful, that's not always true. All right. So we've got our two components there. This thing is touching the table. So because this thing is on a table and it's touching a table, there will be a normal force from the table. Assuming the table or floor is flat, the normal force will have to be perpendicular to that. So the normal force on this thing will have to be going up. So what I can do from here to find my normal force is think about the direction that the normal force is in. We can set up an equation for x, we can set up an equation for y, but I'm only going to use the equation for y to get the normal force, or at least I'm going to start there, because the normal force for this problem goes in the y direction. So for A, let's look at our y equation. Our net force in our y equation is going to equal all our forces added together. The way I write this when I've got variables is if it's up, I make it positive, if it's down, I make it negative, and just make sure you list out every force. So we've got our normal force, we've got gravity, which is going down, so I'm going to make it negative. Again, I'm just skipping straight to mg. And I've got my force 1 in the y direction, which is going up. So this is F1, this is F1y, this is F1x. The y and x means which pieces of F1 we're talking about. Now, specifically because it's not going through the table, I know that this should probably equal 0. If I am doing this out and I get a negative normal force, what that means is that the thing is being lifted up more than it's being pulled down, and that the normal force would have to pull it down to keep it so that the acceleration would be 0. That means you've done the problem wrong and the acceleration shouldn't have been 0, and there should have been a net force, basically. So just watch out for if you get a normal negative net force, double check your math. Once you've double checked your math, double check your concepts. Is it possible that the force pulling it out of the surface is bigger than the force pushing it into the surface? Doing our math out, we're trying to solve for Fn, so we need to add mg to both sides and subtract F1y from both sides. So plus mg minus F1y. So that'll give us that normal force is equal to mg minus F1y, which if I put in my numbers, my m is 40, my g is 10, and I figured out that F1y is 32. So we'll have 400 minus 32, which gives us 368 newtons. Positive. Because we're lifting up on the object, gravity isn't smushing it into the ground as hard as it used to. We're canceling out a little bit of that. So it doesn't have to get pushed up by the same amount as gravity. Anytime you pull up on something, the normal force on it from the ground will get smaller. Anytime you push down on something, the normal force from the ground will get bigger because the normal force is stopping it from going through the thing, which is going to be based on how hard it gets smushed into the thing. All right, B. Finding our net force. Well, we know that our net force in our y direction is 0, so we're halfway there. Now we just need to find our net force in our x direction. To do that, we need to take all our forces in the x direction and add them together. If it's going to the right, make it positive. If it's going to the left, make it negative. So what are all our forces in the x direction? Well, we've got a 38 Newton force from force 1 in the x direction. That's it. We're done. So we just have to plug in our numbers. That one was 38 newtons to the right, and we're done. If there were multiple forces, you would add them up. So hopefully that makes sense. I'm pretty sure that's the end of this one. Great. Yep. So thank you, and goodbye, YouTube.